Howdy, howdy. All right. Well, thank you very much for inviting me to tell you about some of the research that we've been doing here at Texas A&M over the last decade or so. So I'm going to briefly motivate the talk. Can you even see this laser pointer? Or is it too? We don't have any another one, so I'll have to do, I guess. A little bit of a motivation. Then I'll review sort of the observational methods for measuring the Hubble constant. Then I'm going to briefly discuss other cosmological probes that gives us confidence that this tension is real. And then Louis is going to explain what the heck all of this is, right? So the important part comes at the end. I try my best to stay away from astronomer units because I know this is a joint department. I apologize in advance if I missed a couple, but these are basically the relevant numbers. And so when we talk about luminosities in astronomy, we mean the power radiated by a star. And sometimes we talk about flux. Those are really the only things you have to remember. And the megaparsecs are sort of the most useful unit for extragalactic work. It's obviously 3 million light years, or about 10 to the 22 meters. So Nick already mentioned, well, no, he was a grad student, but a century ago, what did we know? We knew that the Earth, well, more than 100 years ago, we knew that the Earth was at least 1 billion years old from radioactive decay of uranium, for example. But we still thought that the universe was just the Milky Way, right? In fact, 100 years ago, the word galaxy did not exist. Right? There was one galaxy, the Milky Way, basically. Or galaxies, I guess, did not exist. People talked about nebulae, these sort of fluffy things that were all over the sky, but they were certainly within the Milky Way. That was the universe, after all. And this universe was not expanding nor contracting. It was simply rotating, which seemed very odd to Einstein, and thus he put in the famous lambda in his equation. So if you ever have the pleasure of going to the southern hemisphere, and this is the type of view that you can see, here's the plane of the Milky Way. Here's the Southern Cross, my favorite constellation. This is the large and small Magellanic clouds, two of the satellite galaxies of the Milky Way, of which there are many. In the northern hemisphere, though, we see another example of a nebula. This is the Great Nebula in Andromeda. And 100 years ago, this fellow, Vesto Slipher, was the first person to measure the Doppler effect on the light coming from this object. And he found that it was actually coming towards us at a fairly large velocity. This is his measurement from 100 years ago. This is the current measurement, not bad. And he also applied the same technique to more distant, or to at least, shall we say, smaller nebulae, at least at the time that he was doing these experiments. For example, here's one, looks a lot fuzzier than the one I just showed you. And from the absorption lines of calcium that you can see there, those two black lines, he derived an apparent recession velocity of 200 kilometers per second. This is much larger. If you look at stars within the Milky Way, which people have been doing maybe for about 20 years at this point, you had some stars coming towards us, some stars going away from us, typically, say, 100, 200 kilometers a second. Why are these nebulae all receding from us, and why are they doing so at much larger velocities? People already had an inkling that these were objects outside our Milky Way, but there was no proof. The same year, 1912, Henrietta Swan-Leavitt publishes this, not particularly nice-looking relation, but it turned out to be one of the seminal discoveries of 20th century astronomy. What is being plotted here is the period of variation of a specific type of star that falls within a family. The first one to have been discovered was in the constellation of Cepheus. So these are known as Cepheid variables. These objects that she's looking at are all in one of those two satellite galaxies of the Milky Way. Thank you. The small Magellanic Cloud. And, oh, yeah, much better. And so what she sees is that there's a striking relation between the period and the flux from these objects. Since all the objects are at the same distance, then you can assume that this is basically a correlation between the period of variation and the luminosity of the object. Now, people tried to figure out what this was. They were clearly not binaries, which were the only type of variables known at the time. This is what Henrietta Leavitt was seeing, right? So here we're seeing 2 cycles of variation for the same object. You see a fairly sharp rise in flux, followed by a slower decline. This is sort of a blue light, if you will. This is what she could do at the time. Now, with modern technology, we can, of course, measure this at multiple wavelengths, and we see a sort of similar curves, although they're getting flatter and more sinusoidal as you go to the near infrared. Now, 100 years later, we know that what we're looking at here is a very brief, just 1% of the life of a star that is much more massive than our sun, at least 4 times and up to 15 times the mass of the sun. And what is causing this variation is basically, well, first of all, Why is the flux changing? It's because the temperature is changing and the radius is changing, right? And so these two things combined, of course, give you a change in luminosity. What's making those changes is basically cyclical variations in the amount of helium that is either singly ionized or doubly ionized. And this acts sort of as a piston that is moving a few percent of the atmosphere of the star in and out. I didn't mention because I was going too fast, but you can see here that the periods of those variations are of the order of 10 days. That's a logarithm of periods, so 10 days, from about 1 day to 100 days. So 1912, we don't know what these things are, but we know that they obey this relation. So one thing that distinguishes, I think, astronomers from physicists is that we don't need to know how something works. We can just use it. We're shameless, right? So this fellow, about 13 years after Henrietta Leavitt's discovery, finds the same type of objects. Admittedly, these are not as beautiful as the light curves I just showed you, but they're basically the same variation. You can see that sawtooth pattern. But he finds him in this object, this nebula, that until then was assumed to be within the Milky Way. And because these objects are much fainter than those seen in the Milky Way or in the Magellanic Cloud, he proves that this object is actually not within our galaxy, but rather at least 10 times farther away. And therefore proves, this is Edwin Hubble, proves that the universe is actually full of galaxies. Now, just around that time, people were using other techniques to figure out the distances to some of these nebulae. And at least 3 people, seen here, Lundmark, Lemaitre, and then Hubble, plot this type of graph, or at least do the calculation. So what we're seeing here are the apparent velocities of those nebulae based on the Doppler shifts that mostly Vestos-Leifert measured, and then distances. It could be through Cepheids, through the work of Henrietta Leavitt and others, or through other techniques. There's not a terribly good correlation, but a correlation nonetheless between distance and apparent velocity. And it was Lemaitre who realized that this could mean that the universe was expanding, right? That the space between galaxies was stretching, and that there was a first day in the universe. Primeval egg, he called it, because Big Bang, the word Big Bang wasn't invented for another 30 or 40 years. So 1929, okay, this is less than 100 years ago. Of course, when Einstein finds about this, he says, why did I put lambda in that equation to keep the universe from expanding or contracting, right? He called it his biggest mistake, but of course, as we now know, was one of his greatest insights. All right, so now today we recognize the work that Lemaitre did before Hubble. Hubble got all the publicity. I guess he had the better Twitter of the day, which was the Proceedings of the National Academy of Sciences. But the Hubble-Lemaitre law basically tells you that there is this constant of proportionality between the distance of an object and its apparent velocity. And if you look at the units of this, astronomers, we say kilometers per second per megaparsec, but of course kilometers and megaparsec are both units of distance. So if you take that out, you basically end up with units of inverse seconds. So in other words, the Hubble constant to first order is 1 over the age of the universe. And this is why Hubble used this in 1929 to sort of estimate that the universe was about 2 billion years old, give or take 10%. He was a little bit off, but it was a good start. All right, so now that we know that we live in an expanding universe, right, you can sort of solve, GR basically using what's called the Friedman equation, and come up with a formula that I'll show you in a minute. It looks a little nasty, but we'll go through it fairly easily. This Hubble parameter, right, h, is then the scale factor of the universe, right? So relative to some time, how was the space between galaxies stretched at that point in the past? A is 1 today, and it was 0 at the Big Bang. And then how is that scale factor changing as a function of time? So that's the Hubble constant, right? A dot over A. Now, if you want to say, if you want to calculate what was h at some point in the past, then you have to use this equation. All right, so we have the square of that Hubble parameter. And you can see several terms here, right, that have to do with the contents of the universe. So matter, right, how much atoms and dark matter there is in the universe will influence how the expansion of the universe proceeds with time. So will, for that matter, the amount of light or neutrinos, right? Or if space has a certain curvature, then you have to take that into account. Even if there's a fluid with a different equation of state, you want to put that in there as well. So we already talked about that. Just to briefly mention that when astronomers use this uppercase omega, what we mean is what is the density of something relative to the density that would require to eventually halt the expansion of the universe, what we call the critical density. These are the other terms that I already alluded to. Note this one in particular. I'll get to it in a minute, I guess. First, what is this 1 plus z that you're going to see in some of Louis' slides? I try to stay away from that in mind, but it's basically 1 over that scale factor that I was telling you about. So a z of 0, which is today, the scale factor is 1. So this fluid that could be in the universe, right? If it has an equation of state, which is basically the ratio of pressure to density, with this constant here being -1, that would mean that it does not change, right? -1 over here plus 1, so that's 0. So it would not change as a function of redshift or scale factor of the universe. And this is, in fact, the famous cosmological constant that was discovered, well, I guess we're closing on 25 years. Huh? All right. So how do we actually measure the Hubble constant? So we have to start with one or preferably more than one galaxy that has a very precise distance. And I'll describe 3 ways that we can measure distances to stars or galaxies in a few minutes. The reason you will have chosen this galaxy is because it has some type of object, in this case a Cepheid, for example, that obeys an easy-to-spot relation, right? So we're going to figure out the luminosities of these objects, and then we're going to use them as relative distance indicators to figure out how far away other galaxies are relative to whatever our anchor is. So when we step away from these nearby galaxies to more distant galaxies, for example, in the work of the key project that Nick alluded to, Rob and I and all the other members of that team could only use the Hubble Space Telescope to cover a very small portion of a galaxy and find a few Cepheids. So that's why this relation is not as well populated as the one below. The scatter may be larger because our observational uncertainty is also larger. Note that here we're measuring fluxes, okay? And over here, because we know the absolute distance to this galaxy, we have measured luminosity. So of course, the difference between these two will be given by the inverse square law, right? So that allows us to figure out the distance to that galaxy. Now, when we measure distances to galaxies using stars, if we only look at one particular wavelength of light, we need to remember that there is dust in space. You can even see it here in this spiral galaxy. And dust, of course, will attenuate blue light more than green light and more than red light, leading basically to what would appear to be a different distance depending on the color that you're using. But because we know how dust works in the universe, we can do observations at multiple wavelengths and then take that out and obtain what is truly the unbiased distance to the object. Why have we chosen this galaxy in particular? Well, this one in particular we chose for 2 reasons. First of all, the entire galaxy, the luminosity of all the stars in this galaxy, is correlated with the rotation velocity of the galaxy. Basically, the gravitational well, right, in which all these stars live, also, has some amount of light, and there's this very nice relation called the Tully-Fisher relation, discovered more than 30 years ago, 40 years ago, I guess now. That little dot that you can barely see inside the red circle is one of the supernovae that Nick and colleagues have been observing for many decades. And we know that those objects are almost always the same luminosity. There's a slight difference based on some other properties that can be characterized. So these are what we call secondary distance indicators, right? They're too far away for us to measure one object absolutely, but we can calibrate their luminosities based on the measurement of another technique. So that's why these are called secondary distance indicators. Once you have done this calibration, though, because you have luminosities, now you can apply them to galaxies that are much, much farther away. And typically, we want to look at things that are at least 100 megaparsecs, or 2 times 10 to the 24 meters, because by then the expansion of the universe is dominating over any random velocities that the galaxies may have due to gravitational attractions. So this is a very, complicated method to get at the distance of a given galaxy. Now, the velocity today we can measure in about 10 or 15 minutes. It will take light for 3 nights to measure one redshift. And then if you take the ratio of these quantities, you get the Hubble constant. All right, so going back to the Cepheids for a minute, if you look at Cepheids of a given mass, I told you Cepheids are in a family of objects, right? So they change in period as they evolve. They also change in luminosity. But because there are many objects of this type, we have this nice relation between mass, right, which is the proxy for luminosity, but it also gives you the period of the object. And you can see here sort of back on the envelope calculation as to why that is. It's basically the crossing time of a disturbance through a star, and you need to know the sound speed of the gas, and then The only thing you need to measure from astronomy is basically the relation between radii and luminosities, and then you get this scaling between periods and luminosities, which is the line that is traced there. But note that this has an irreducible width due to the physics, right, to the evolution of these objects. So you can't just use one Cepheid to measure the distance to an object. Well, you could, but that measurement will be quite uncertain. So you want to get many, many Cepheids in a galaxy. Here we see the Large Magellanic Cloud, one of the two satellites, largest satellites of the Milky Way. And we see, I don't know, about 1,000 Cepheids pulsating and obeying this so-called Leavitt law in honor of Henrietta Leavitt. The relation is broader in blue and green wavelengths due to the effects of dust, to the fact that Cepheids span a certain range in temperatures. As you move to the near infrared, the relation becomes much, much tighter, and so it's a better distance indicator. But if you recall 20 slides ago, by the time you get to this wavelength, Cepheids are hardly varying. Right? So in order to discover them, you need to look at them in optical light. But then when you actually want to make the distance measurement, you want to switch to infrared light. All right, so how do we actually get the luminosities of Cepheids? Okay, so we need to know, I told you, absolute distances. Well, we can measure absolute distances to about 20 Cepheids within the Milky Way at the moment. This is using parallax, the fact that the Earth goes around the sun, right? If you know the size of the astronomical unit, then you can do that. This will increase thanks to a lot of work by European astronomers mostly in a few years. The Large Magellanic Cloud is a nearby galaxy that I told you about. Well, there basically you can use the fact that stars are black bodies, right? And get a very precise distance to that object as long as you know a few other things about the stars that you're using. A completely different technique. This is, by the way, independent of parallaxes. A completely independent technique is if you look at enough galaxies, and most galaxies, as we know from Journal's work and others, have supermassive black holes in the center. In a few cases, you will find water masers that are orbiting this object, basically perpendicular to the line of sight. So you can follow their motion for about 20 years. This is not easy to do by any means using radio telescopes spanning the entire Earth. But you can then get a very precise sort of 1 or 2% distance to those galaxies. So 3 completely independent techniques. We can see them here. On purpose, I took the units away because they're in astronomer lingo, and you don't really need to know that. But these are all Cepheids within the Milky Way, each one at a different distance, of course, because they're within our galaxy, but we measure parallaxes to them. These are all the Cepheids in the Large Magellanic Cloud. These are all the Cepheids in that supermassive black hole host galaxy. And here we're basically measuring their fluxes. So the ones that are closest to us are brightest. The ones that are farthest away from us are faintest. Why are they at the top? Because we're astronomers, and we want to keep all the physicists confused. So fainter objects appear on the top in this case. But the point is that this relation is basically the inverse square law, right? That is not that slope is not being fitted for. It's known. And so you look at the residuals along this relation, and you can figure out how well you have calibrated the luminosity of a Cepheid. So this is the entire basis on which this ladder builds up to the point where you look at other objects. I already told you that little object over there was a type 1a supernova. It doesn't look very impressive, or a white dwarf supernova. It doesn't look very impressive in that picture. But here we see a much nicer example where this one, perhaps couple of white dwarfs, perhaps a white dwarf and a companion star, are basically outshining another few billion stars, right? And again, you want to look at these things at multiple colors, say blue to infrared. You want to follow them for, as you can see there, a few months. But eventually, if you do all these measurements, you can correct them all basically to the same standard, right? And then for any given supernova, you can get sort of a 7% distance to its host galaxy. What's going on here? Well, you already read faster than I can speak. Basically, these objects are detonating or deflagrating and turning a whole bunch of carbon and oxygen into other elements, and it's that radioactive decay or several radioactive decays that are powering this light curve. Here's a few thousand supernovae. Again, at different distances from us, we can basically figure out the scale factor that the universe had back then. And so we're going all the way back to 70 or 75% of the age of the universe. And all these supernovae are falling like beads on a string. This is thanks to many surveys. You can see different colors for different surveys, but especially the work of Dan Skolnick, who put all these different surveys from different telescopes on the same system. A lot of careful work went into that so that the dispersion in this relation is tiny, a few percent. And this is by far the best method that we have for measuring distances to other galaxies. So that completes the distance ladder that I was telling you about before. Okay, Cepheid period luminosity relation, anchored with an absolute distance to a galaxy that hosts a supernova, so that you can go to farther away galaxies and get the slope of that relation, basically the Hubble constant. How do we measure distances to these galaxies? Well, the Hubble Space Telescope is the only telescope that can do that type of work, at least at the moment. Here we see a gorgeous image of two spiral galaxies that are merging to become, hopefully, an elliptical in a billion years or so. These are called the antennae. When they hosted a supernova, it was sort of somewhere outside of the image in 2007. Here's another galaxy, more perhaps like the Milky Way, that hosted another supernova in 2007. So the reason that we picked these galaxies is because they were hosts of these types of objects, and then we are reassured by the amount of blue stars that we're going to find Cepheids within them. Otherwise, we can't use them. In total, we have 19 of these objects. All these you will recognize are basically more or less face-on spiral galaxies, in some cases interacting galaxies, with copious star formation, meaning that we're going to find these relatively young Cepheids. These Milky Way, Large Magellanic Cloud, and NGC 4258 are the three galaxies to which we know the distances very well. We use Andromeda sort of as a supporting actor, if you will. And this is basically what sets the foundation for measuring the Hubble constant. In each one of these galaxies, we'll find Cepheid variables. Sometimes nature is very cruel and only gives you 4 Cepheids. Sometimes you get more Cepheids than you know what to do with. But for each one of these galaxies, then we have a distance that is good to a few percent, and by averaging over 19, then we can measure the luminosity of supernovae to a few percent. As of 2011, we had done this to 2.5%. Now we have, this is with an old sample that only had 9 supernovae or so. Now we have 19. And so again, the scatter of this relation is perfectly consistent with the uncertainties given by Cepheid distances. So we know that there are no systematics in this part of the diagram. And again, inverse square law tells you what trend to expect. Then you go to the really distant supernovae, which there are much larger samples. For this type of work, perhaps we use, say, 200 supernovae over here, but there are, of course, many, many thousand, which allow you to also solve for the cosmology of the universe. We really haven't talked about that yet, so I better hurry up. So what is the current best value of the Hubble constant? Well, in astronomer units, is this, 73.5 kilometers per second per megaparsec. This is in, if you turn it into SI units. The total fully propagated uncertainty is below 2%. That's basically a slight improvement from these two papers that gave 2.5%, 2.4%. But in the few intervening years, we've done incremental improvements, basically to the absolute distances to either objects in the Milky Way, the Large Magellanic Cloud, or the host of the supernova of the supermassive black hole. This will go from 19 to about 35 in the next year or so. Work being led by my former grad student and currently a postdoc at Space Telescope, or at Johns Hopkins, I should say, Wenlong Yang. So that's the Hubble constant. But there are many other probes of the universe, right? I'll briefly mention a few because they'll become important to make sure that this discrepancy that we're going to talk about is not just a random fluke due to some systematic uncertainty, say, in the supernova work or in the Cepheid work. We already talked about white dwarf supernovae. You've seen this diagram. Here is just a couple of the most distant supernovae ever seen when the universe was barely 40% of its current size. It allows us to solve for the cosmology, right? What type of universe do we live in? For example, if we assume that we live in an empty universe, then we would expect a certain relation between distances and fluxes, or scale factor and distance. And we don't see that, right? This would be if you live in an empty universe, the dashed line here going through the plot. What you actually see from the supernovae is this red line. The original work from 1998, I think, was based on 2 points. That got you the Nobel Prize, right? Things have improved a bit since then. So we know that we live in a universe that is actually dominated by this cosmological constant. Einstein came back from the dead, was very happy that he hadn't screwed up after all. It was supposed to be a joke, but anyways, I'll move on. So if the universe started at some point and everything was hotter back then, we might expect to see some of that initial radiation. We may even expect to see some fluctuations within that black body emission due to, say, initial fluctuations that were present after inflation. An important fact that was already thought about in the 1970s is that because these photons are coupled to the baryons, they're actually oscillating for the first 379,000 years of the universe. And so they actually contain information that can be used to figure out what was happening back then. So we'll talk more about this because Luis has quite a few slides on the cosmic microwave background. I'll just say that it wasn't that long ago that we first saw the black body spectrum, right? The peak of the black body spectrum from the cosmic microwave background. It was even not even less long ago that we actually measured these fluctuations for the first time with any signal to noise. These are supposed to be the same maps, right? But here you can actually see those temperature anisotropies. And it was just a few years ago that not only could we measure those temperature anisotropies to much higher angular scale, but we also measure anisotropies in other observables, like the polarization of the cosmic microwave light. And so that line that goes through the points there is a best fit cosmology that assumes that we live in a universe dominated by dark energy with dark matter. And there's a few other parameters, but there's only sort of 6, 8 of that order that you're solving for. So note that dark energy was negligible at that time because that grows as the universe, or it becomes more relevant as the universe grows in size. And back then, the universe was less than 1,000th of its current scale factor. So what does the cosmic microwave background tell you? It tells you that you live somewhere along this line, okay, in terms of how much matter there is in atoms and dark matter, and then how much the cosmological constant contributes at this point. Supernovae tell you that you live in a universe somewhere over here. So presumably where these two meet, which is that green ellipse, is where we are. But notice that the Cepheids and the local supernovae tell you that you actually live in a universe that's somewhere in that red band. So then those two don't quite match. That's basically that tension that we're talking about, although it will be much more apparent in a couple of slides. As a little side note, right, there is no reason why the cosmological constant has to be a constant. It could be that dark energy is evolving. And one of many parameterizations would be that it evolves with the scale factor of the universe. And so that's something that astronomers have been trying to measure since 1998, right? And we cannot do it very well, right? At the moment, the uncertainty on that derivative is of the order of 60%. So, but we'll get a lot better, say, within the next 15 years or so. So I told you about these waves that are basically imprinted in the power spectrum of matter due to the coupling of photons and baryons. Once the photons free stream, then that signal is basically imprinted in the matter. And so if you do a large-scale redshift survey, this is 11 degrees in the sky, so you basically need to cover a very large chunk of the sky before you can extract this signal. Then you will see a peak that I'll show you on the next slide. What sets that angular size can actually be calculated fairly easily. All you need to know is the speed of sound in that photon baryon fluid. And that is, if you assume that you live in a certain cosmology, then you can actually measure that or calculate it pretty well to less than 0.2%. Now, galaxies have moved since back then, so that initial pristine feature will have been slightly blurred by gravitational attractions, but you can sharpen that feature again because you know where all the galaxies are after all. And so this is the type of signal that you get from this so-called Baryonic acoustic oscillation. Okay, that extra peak, it looks huge here, but they're multiplying by s squared. So in fact, this is a tiny, tiny signal. You can measure that at a variety of scale factors and then solve for a cosmology. And that's how this is used as a so-called standard ruler. So to recap, you look at the cosmic microwave background, times 0 almost, right? You assume that you live in a certain type of universe. That allows you to calibrate the size of that feature. Then you go and you measure it at a variety of scale factors, and then you fit this red line. Okay, this is the sum total of all the measurements that have been made with this technique. So it's a very difficult measurement to make, especially when you get to higher redshifts or earlier in the age of the universe. But it allows you to predict what that Hubble parameter ought to be today, okay, to 1% or so. And so that number in astronomer units will be like 67.4 or so. When you actually go and you do the measurement with the Cepheids and the supernovae that I told you about, that's what you get. Okay, and that is the uncertainty. That's, well, the current uncertainty. In 2016, it was 2.4%. That error bar that I drew by hand is 1.9%. And that discrepancy is about 5 sigma. So put it in another way, these are the ranges of Hubble parameter that you would expect based on the cosmic microwave background and Baryonic acoustic oscillations. And this is our PDF, well, or was our PDF back in 2016. Now it has tightened up a bit more. So that is not a very large amount of overlapping values, right? And that's what we refer to as a tension. Note that it doesn't really matter how you calibrate the Cepheids. You basically always get the same answer within the expected variance from the uncertainties in each technique. This was as a year ago. And so one problem you have is that you have two methods, one based on the early universe, one based on the late universe. Maybe we both screwed up, maybe nobody did, but it would be nice to have an independent confirmation that this is indeed true. Now, do we live in a bubble? Could we be in an under-dense region of the universe that makes our expansion faster than the rest? No. We have very, very good redshift surveys, one that's coming up in a few days. But based on other ones, even looking at supernovae samples, we know that we only expect sort of a 1 sigma variation in the Hubble constant of 0.6%. Okay? And the discrepancy between what we measured and what is predicted is 9%. So it's not going to come from bubbles. So what is a way to prove that this is indeed a true discrepancy? So you can look at the light coming from quasars. These are sort of, again, black holes that are growing very fast in the early universe. Light comes from them. Sometimes it goes through another large mass. Could be a cluster of galaxies. Could be one galaxy. And basically now every photon will take a different path. And so when you look back, say, with the Hubble Space Telescope, you'll see multiple images, right? And you can use the distances, the relative distances between these things to, once you measure the potential, basically, to infer the Hubble constant. Completely independent, doesn't know anything about Cepheids, supernovae, right? It just knows about GR. And yeah, there's a lot of pieces to it. You have to measure the delays in these quasars as they feed on nearby matter. You need to map the positions and the relative fluxes and do all these measurements. But this is again another very large endeavor requiring many, many telescopes, a lot of detailed work. The nice thing about what they do, they're able to set this up in a way that the measurement is blinded, right? So they don't unblind until the moment that they're ready to submit the paper to the journal, which is really nice. We don't blind, but we actually don't look at the number. What we're obsessed about is the uncertainty in the number. But they do completely blind analysis, and they get exactly the same answer as we do. So we get 73.5, they get 73.3. And again, because these are completely independent techniques, you can combine them, and that 4 sigma discrepancy now turns into something like 6 sigma. This is a plot from earlier this year from one of the papers from these gravitational lensing people. Here you can see the early techniques, right, relying on the cosmic microwave background and the assumption that we live in a lambda CDM universe, compared to things that you measure either using stars, gravitational lensings, or just plain cosmic expansion from galaxies that are sufficiently far away. This is a revision to a technique that perhaps was plagued by systematic effects by my former grad student. So if you look at all these numbers, they're basically entirely consistent and give that sort of 5-6 sigma discrepancy relative to the prediction or to the expectation. So that's where the observations are. What can we do? Well, we need more supernovae. We have done every supernova that the universe has provided to us since 1985 or something, so we're waiting for more supernovae to blow up. We need about 50 of them. We have 35 at the moment. They only occur about maybe once every year and a half, so we probably will not get to do 50 by 2022, but what's really important is these parallaxes to hundreds of Milky Way Cepheids by the Gaia mission, and that will really get us quite close to this 1.3%. Although I think by now it's less important to do that because we have all these independent techniques that are yielding the same answer. Which I already listed here. So we have this tension, at least 4 sigma, perhaps 5, perhaps 6, depending on what you want to combine. Is this new physics in the dark sector? And if so, what new physics can you put in that doesn't break all the constraints from other observations? Louis will explain. No, let's do it at the end. Oh, we can plot now.
Oh, thank you. Okay. Oh, yeah. Okay. Okay, so I've got maybe 10 or 15 minutes or so. I won't take too long. So I will. So my caveat here is I haven't really worked on this subject in a while. I wrote a few papers on this in graduate school. So I guess the lesson is if you're a graduate student, what you work on could come back to haunt you a mere 15 years later. So don't forget that. But this is a good talk I can give because I can just disparage everyone else's work. But actually, I won't do that. What I thought I would do here is sort of unpack the cosmic microwave background aspect of this measurement in a little more detail. So I'll spend the first few slides really hammering a little bit more home what we're measuring when we measure the cosmic microwave background, and then go through some possible new physics solutions that could alleviate this issue here. So let me remind you again. So here is a model for the evolution of the universe. Mere 13.7 gigayears ago, the universe was a much hotter, much denser place than it is right now. There's lots of key epochs that the universe goes through. Initial period of inflation, Big Bang nucleosynthesis when all the light elements were created, the creation of the cosmic microwave background, which I will focus on here for a couple more slides, and here at Redshift 0, which is where Lucas lives in space-time and where mostly he talks. Let me just remind you that as you go back to earlier times in the universe, you're looking back, objects are redshifted. These objects here, the redshifts we'll be talking about for the cosmic microwave background are characteristic of twiddles, something like redshifts of, thousands or so. So that's the area that I'll be living in here. Okay, very good. So the standard cosmological picture here we have various cosmological probes in the universe, some of which Lucas talked about. I won't go into detail on all those. Give us sort of the standard cosmological picture for the energy budget of the universe. Dark energy is about 72%. Dark matter is about 23%. Everything we measured in the standard model is less than some odd 5% of the universe, and these are all sort of the particles that we know and have identified in nature and have identified their interactions. Let me just highlight there's 3 flavors of neutrinos. I'll come back to that in a few minutes here, because that's possible. Kind of fiddling in this sector is possibly one of the way out to this issue. Let me just remind you also that back around the epoch of the cosmic microwave background, some 380,000 years after the Big Bang, the cosmological pie was a little bit different if you baked it. So there's about, at that time, there's about 63% dark matter, neutrinos and photons, 10 and 50% respectively, and the atoms that we know about. Something like 12% of the universe. So there was dark energy, of course, is kind of turned on here later in the universe. So let me talk for a few minutes here about the cosmic microwave background. So this is kind of going to be a 101 tutorial. I know lots of us in the room don't think about the CMB very often, but let me kind of remind you, the CFB is basically the most perfect black body that's ever been measured. What you do is measure temperature at different points in the sky. Measure the frequency distribution here to extract the temperature, I should say. And what one finds here is what one averages over all locations in the sky. One gets more or less a perfect black body at this stage up to our experimental precision with a temperature of about 2.725 degrees Kelvin. So it's very cold. Also, one thing you can do, you can look at the root mean square temperature fluctuations at different points on the sky. So basically take the temperature at some point, subtract it from the mean, divide by the mean, and do that all over the entire sky, and take that average, and then you get a root mean square temperature fluctuation of about, 1.1 times 10 to the minus 5 here. And so here's this map here of these temperature fluctuations here from the Planck satellite. And Lucas showed you in the early days of this measurement, this was actually much more coarse, and now this is a much higher resolution image of this map. And I believe this showed on the cover of the New York Times back when it came out. Something like the universe's baby pictures was its highlight. Okay, so those are 2 key scales here. So once again, let's just go through what's going on in the cosmic microwave background. Okay, so that's the empirical measurements. Okay, so why do we have this microwave background? So back when the universe was a hotter, denser place, greater than redshift, about 1,000 or so photons and electrons scattered off each other very frequently, more frequently. Well, they essentially don't do that today, cosmologically speaking. So we could approximate this photons and electrons as a photon baryon fluid in the early universe. And at some point, the universe started to cool down as it expanded. Electrons combined with protons around the area of recombination. Photons then started to free stream to us, right, essentially from that redshift. So anybody here in this room is an observer, and you're filled around with a cosmic microwave background, which reflects the time when the universe became transparent. And so sort of the last scattering, if you will, that a cosmic microwave background photon underwent off an electron approximately is called the last scattering surface, okay? So very good. So there's another interesting point here, which sets up these temperature fluctuations. And this diagram here is thanks to some cosmology tutorials from Wayne Hu. So basically what you do is this photon baryon fluid is fluctuating in and out of gravitational potentials, okay? So these temperature fluctuations you can break up into modes of given wave numbers, as is shown here. And the key point here is that you have these temperature fluctuations which correspond to this fluid oscillating, right, coming out in and out of these potential wells. And these fluids have these oscillations sort of have different length scales associated with them. Okay, so there's one particular special length scale, right, that shows up, and that corresponds to a fluctuation that that traveled and was sort of maximally compressed at about the time of the last scattering surface. Okay, so that corresponds to approximately how the sound horizon in the early universe, and that gives us here the first peak in this acoustic in this temperature fluctuation spectrum of the cosmic microwave background. And then going on here, you have sort of higher level harmonics of this background, sort of as you count down to what's here, larger angular scales to smaller and smaller angular scales. Okay, so that's a bit how that works. It gets damped. I won't explain why it gets damped here. We can come back to that later if you're interested. Very high, or very high L's, or sorry, very small angular scales. They're high multipole moments here. Okay, so the key thing is here. This is just the key thing here that you need to remember out of this sort of quick lightning round study of the CMB. So the location of the first peak here measures the ratio of the sound horizon at last scattering to the angular diameter distance to the last scattering surface. Okay, so really any solution to this issue, right, really just changes one of these two things in some way, right, from the standard cosmological picture. So I'll go through a couple of solutions that change both of these in a few minutes here. And I should just mention that, so there's the 6-parameter cosmological model that Lucas mentioned that Planck extracts. Planck uses this data to extract the parameters for. So essentially the baryon density, the dark matter density. Here's the value of this first peak here as well. And there's a couple other parameters we don't really need to worry about right now at this moment. But the key point about the CMB, this is the data here, right? Okay, or this is part of the data. And it fits this cosmological model and gets these parameters from this data, okay? And that's how it does it, right? So in some sense, it's less quote-unquote direct, if you will, than what Lucas is talking about. All right, so here's a figure that Lucas showed as well. So this showed up in the Planck collaboration paper from 2019. So measurements of the Hubble parameter as a function of redshift. So this is once again going earlier in time. So there's the measurement that Lucas was talking about. These measurements here are from so-called baryonic acoustic oscillations. I won't go into the physics of those in too much detail right now, but these sort of anchor this measurement here at sort of intermediate redshifts, if you will. All right, so the question is, how do we sort of reconcile these two measurements here? And I'll try to go through a few of these models in the last 5 minutes or so about how this is done. So this is just sort of a reflection of me going through the recent literature and trying to assimilate what's been going on here. So I don't really have a dog in this fight as a theorist. Sorry, so.
And I'll say one thing, right?
Yeah.
So it's how do you reconcile one measurement with one prediction?
Prediction, you say.
Because the 68.
So that's a predict. So you're saying that that's a prediction right there. Okay. Okay. So a model. This is. I would actually call this a model which describes the CMB data. Okay. Okay. Okay, so so early time solution. So there's two flavors of this, right? You know, you change the sound horizon or you change the angular diameter distance to the last scattering surface. So the former of those, the sound horizon, go under early time solutions to this issue. And basically, what you want to do here is reduce the size of the sound horizon at approximately time of last scattering. And so one way to do that, which has been written about by a series of authors in the past few years, is sort of turn on a dark energy component early in the universe. Okay, so we had a late time dark energy component, which you know about. So why not turn on something earlier? So there's a field here. So this is the density of all these components. This is the scale factor. So this is today here. This is earlier on. So let's see, matter sort of redshifts away, sort of in a standard way, like 1 over the cube of the scale factor. Radiation here, so photons redshift away like 1 over scale factor to the 4th power approximately. Then what you can do is you can bring in, so here's the cosmological constant down here as well. So then what you can do is you can bring in a early dark energy component that behaves kind of like a cosmological constant early on, and then becomes dynamical at some characteristic redshift, evolves at some potential, and then it starts to redshift away much faster than radiation. The idea then is that this contributes a very, very negligible amount of the total energy density today, but at some point it actually mattered a lot. Okay, so the net effect here of this solution here was to reduce the sound horizon at early times, okay, which would help solve this problem. Okay, so I won't go into too many details about this. It's about 450, and we don't need to talk about fluctuations and fields on different scales. But the idea here is that this model actually, so you can have this field. It doesn't fluctuate on small scales. It fluctuates on very, very large scales, sort of like horizon-size scales. And you can see imprints of these fluctuations on horizon-size scales in that very, very high L or low angular scale of the cosmic microwave background spectrum. So this actually makes a prediction for this particular region of space that it can actually be tested with future CMB and polarization data. Okay, so that's early time solution 1. Early time solution 2 is the first thing people typically think of when they want to try to solve this problem is to add more neutrinos, cosmologically speaking. Think more in terms of, say, relativistic degrees of freedom in the early universe that, once again, make the universe expand faster early and reduce the size of the sound horizon. So here's the number of effective degrees of freedom here. So 3 is sort of a standard model picture for neutrinos versus H0. So this appeared in the Planck collaboration paper as well. Let's see, here's the measurement from 2018. So the point being here is that this can go part of the way, but really not the entire way to reconcile both of these measurements as well. So that is a story for an early time solution number 2. So let me give you a flavor of a late time solution where you sort of change the distance to the last scattering surface. And I kind of picked on this paper here, which came out earlier on. So earlier in the previous 2 slides, well, in the first couple solutions, I was talking about a dark energy solution, right? Then I talked about a neutrino solution. And now let's talk about a dark matter solution to this problem. So here's a story where you can have dark matter which decays. In this case, the dark matter particle would decay to another dark matter particle and a bit of radiation, but it would decay at kind of an opportunistic time, sort of later in the universe, and then later in the universe in this scale means about giga or so after the Big Bang. And what it would effectively do is it would contribute to the energy budget of the universe sort of after the CMB, okay? And it would modify the expansion rate of the universe at later times, and that's what is shown here. And then, so then Lucas doesn't have to. So this is a prediction, I guess, right? So for this model, so here's a standard lambda CDM scenario down here, and this scenario here modifies the expansion rate in such a way that it kind of gets you closer to the CMB value. So this is a bit of a playground for theorists at this stage, but there are very, very strong constraints on all these scenarios. The baryonic acoustic oscillation scenario that Lucas talked about in these measurements here really constrain a lot of these solutions. My last slide here, like here's the laundry list of theoretical solutions that I found in the literature. Please don't ask me about all of these because I do not read, and I don't know what all of them mean. My particular favorite one to read about was cannibal dark matter. So the flavor here is you can either sort of change things sort of in the dark energy sector, change things in the dark matter sector. You could even modify general relativity, why not? Okay, right, there's more theoretical solution than there are theorists. That's a good thing or a bad thing, I don't know. But really, just I guess the final thing to say here: new physics or systematics, and this is the question kind of sort of we all theoretically inclined people ask when we see measurements like this. And you know, at some point, hopefully, we'll get that measurement that's hinting at new physics. Perhaps this is it, but we'll see. But thanks to all the observers here in the room who've done great work on this. Yes. This one here. Uh-huh. Yeah. Well, this is a. But remember, this was fit to the cosmic microwave background. This wasn't fit to these data points here. Yeah. Okay, I don't exactly know what you're getting at here. Well, okay, so this, I'm not actually familiar with this measurement. This is actually, with the details of this measurement, this is a measurement of the so-called baryonic acoustic oscillation spectrum, basically. Just because you get those fluctuations in the photon baryon fluid in the early universe, you can actually see that imprint in the power spectrum for galaxies. And so basically what those measurements do is they measure the distance to the redshift at which you're measuring that power spectrum. Okay, that was a mouthful. But so yeah, so I mean, I guess I don't have a sense of what the systematics are in these measurements. But I think the key point here is that this is not, this is not a fit, right, to these data points. And as Lucas and friends will tell you, like this is, I think I would probably, well, I shouldn't say anything, but this has been studied a lot more than this, right? In terms of getting the Hubble parameter. I might defer to you for that, if you have any notes.
No, I mean, I would say that, forget about those points if you want. Right. This line, this red line, right? This red line is calibrated at, for this case, factor 1/1,000. And it's propagated to today, right? So it's not relying on these measurements to predict a value, right? And the uncertainty in that prediction is basically the size of that red line. So what you'd want to compare is basically that, red line to that data. That is a discrepancy. Yeah, these data points are here as an illustration, right? But they're not basically giving you they're not related really to this solution. This is based on, it's just another way of probing the early expansion of the universe. You could use supernovae, right? And then you could use something about Big Bang nucleosynthesis, for example. If I show you, right, you can use Big Bang nucleosynthesis plus other measurements of galaxy correlations to infer, to predict what that expansion rate of the universe will be. I mean, that's not as precise as just assuming a certain cosmology and looking at the cosmic microwave background, but these two techniques are basically independent. But they rely basically on the assumption of a certain cosmological model. So that, one way of representing this, if you will, is by drawing that line, right, irrespective of whether those points are there or not. I don't know if I'm explaining myself very well. So this is the sort of the standard cosmological model calibrated to the cosmic microwave background observation. then you go from that very early time to today, you expect a certain value. Then when you go measure it, you measure something that is 5 signal meters. You can also see that in sort of this video. Everything that we know from cosmology, would predict that we live somewhere in the area covered by this galaxy. The measurement and the uncertainty, those are that's sort of the 5 signal experiments.
So I don't actually know what the sigmas are on those VO plots, the VO things of high redshift. I don't know what those are, what the so that's an important thing that we should point out.
Whenever I go to talks on this, except for talks about uncertainties, the CME people don't talk about their uncertainties. It's like perfect. So are there any cracks in the CME physics?
I mean, I guess there's two questions. There's cracks in the like the model of lambda CDM, which theorists are happy to crack. And then there's cracks in, making that map, I guess, right? And I guess, unfortunately, I'm not the person to answer that question about, like, what are the systematics that go into making that measurement.
I think the people of the CMB don't talk about this uncertainties because the uncertainties are smaller than the size of the point. And there have been multiple experiments that map the CMB from the ground, from space, and when you look at them at the pixel level, they all agree excruciatingly well. So the problem is, you can fit, maybe something that we did not mention is you can fit many universes, right, in these same data points. All you have to do is change some part of the physics, right? So if you assume that you live in a universe dominated by dark energy, then that's the fit you will make. But if the model is wrong, then you'll get the wrong answer or the wrong prediction for the current expansion rate. Hence, put in decaying dark matter, put in early dark energy or late changes to dark energy, and you will get a different prediction for the current expansion, but you'll still fit these data points just as much.
Size of the horizon.
The size of the horizon?
Yeah.
Well, it's the look back time to
I have a number for you if you want it.
42.
14,000 megaparsecs. Size of the horizon in the benchmark model. There you go.
But, I mean, the point is, that we keep saying that the age of the universe is 13.7 billion years, give or take a very small uncertainty. But that entire number is predicating on the fact that we assume the cosmological model. If early dark energy is there or something else, then the universe may be just 13 billion years old as opposed to 13.7. So that uncertainty is more like 1.14, right? It's much larger because you're switching from one model to another.
Yeah, remember too, like 13.7 kind of gets spit out of its model fit at some level, right? That's a little bit indirect in some ways, right? So.
Why isn't it conclusive? Why can't you now conclusively say that the model is wrong?
Well, that's I think what we're saying. I mean, so a year ago that would have been hard because this is just based on one technique. And do we know enough about Cepheids? Do we know enough about supernovae? Maybe we don't. Maybe we.
It's not 5 sigma that to a colorful technique at least.
Right. And so that's what what these people do, right? Is completely independent. And because the answer is so similar, and when you put all these measurements together, you get very consistent answer. Then I think we are at 5 sigma. But now it's why, right? And
well, I think if there was if we had a theoretical explanation that kind of made sense in the context of the rest of the whole cosmological picture, people would be glad to say, okay, hey, it's early dark energy, and now I see those little wiggles that it's predicted, and they say, hey, you got it, you're onto that story. But I think as from a theoretical perspective, we haven't actually there's really there's not a huge need right now to change the picture, right?
I think
and it's very constrained when you try to change it.
In some sense, even though the discrepancies from dark energy in 1998 was smaller in sigma, perhaps. People are there's an explanation for that. It's a cosmological constant. So it was perhaps easier to accept. young back then to know, I mean, how many fights they had to go through. But it seemed like it still converged pretty quickly. Dark energy is a thing. Here the problem is, well, who ordered this, right? And so, and what testable prediction can you make to check that? So that's why, yeah, this model with early dark energy actually, fits the data better than lambda CDM by adding at least one parameter. But in terms of chi-square, it's not a very significant change because the error bars are so large. But the testable prediction, like 2024 or so, we will have